So we chatted a little bit yesterday about what this looks like. Okay, conditional probability means given something happened, we called it event A, that's going to determine the probability of this other event happening. Okay, part B. So this formula that we kept talking about looks something like this. The probability of A and B, so both events, over the probability at A. And we kept looking for keywords on this, like given, or sometimes that kind of slash that was there in the parentheses. So when we're looking for conditional probability, sometimes it may be in a paragraph form, sometimes it may be in a table form like it is here. So for instance, our first example, table shows the results of a class survey. Okay, find the probability someone did a chore given it was male. So what we typically had been doing, and they did the totals on the males and females for me, is I total up my rows and columns. And then I start looking to see, okay, how does this work? And I'm not going to follow theirs on the bottom. I'm going to do my own. So here, what I'm going to be looking for is the probability of doing a chore and being male over the probability of being male. Because again, that part after the slash is always my A, and the part in front is always my B. So I look, and I go, okay, well there's 15 males, so that's my denominator. Now up top though, I got to get the two things together. So I find males, and then a chore, yes, says there's 7, and that would be my answer. So it's just taking the little pieces and then putting them together to just make this quick fraction, but not a lot of math. Whoa. That'll be fun to talk about later. Okay, so it'd be the same then if I came down a little further and said, okay, use the data to find the probability of a female given the person did a chore. So again, I get my A and B set up. So here it would be the probability that I did a chore, because that's what's after the slash, after the line. And the top would be the probability of a female and doing the chore. So we take a peek and we go, okay, let's see. Chores, that would be my yes column. So I'd look down and I'd say, okay, so 14 people did a chore. I got that. And then the top is yes in the chore column, but it's also female, which would make it 7 out of 14. Or 1/2. So that slash or that given is always going to be my help on that. Okay, and then it mentions it again down here right below there, what my formula is that we drew up top. So, what we're going to do now, I'll take one peek here. Unfortunately, my question that I'm seeing goes here, starts here and goes to the next page, but we'll remember. Okay, researchers ask shampoo users whether they apply shampoo directly to their head or indirectly using a hand. Find the probability that a respondent applies, spit it out, shampoo directly to their head, given the respondent is female. Okay, directly to the head, given that it's female. So as we flip over, fortunately, we're not going to need all the mumbo-jumbo they have there. So, given female, so my given part that was on the front told me what goes on the bottom. And on the top is, it said, find the probability that a respondent applies shampoo directly to head. So, directly to head. I guess I could have even just called it HF. That's fine. And so I notice, oops, I gotta add up my columns here. So I go, all right, female, 30. Female, directly onto head, 6. And reduce the fraction if I can. But again, if you got it just to this even, I'm a very happy person with you. And the way we do it is much simpler than they're trying to explain it to the left. Like, I have no idea why you would go through all of that when we can just get the information that we need. Okay. Now, here's one thing that could throw a little bit of a twist into what we're doing, though. If we flip over, because I don't think we need that extra example at the bottom. If we flip over, okay, one option, okay, sometimes of these is also to do a tree diagram. So, let me push this up a little higher so we can see the diagram as we're doing it. So a student in Buffalo, New York made the observations below. Of all snowfalls, 5% are heavy. So you'll notice they changed the 5% into a decimal and labeled it with H for heavy. I mean, you could write out the word, that'd be fine too. Which then means the other 95% of the time, because again, these always have to add up to 1 or 100%, is going to be light. So it's like, okay, after a heavy snowfall, schools are closed 67% of the time. Okay, so if it's heavy, it breaks off into closed, 0.67, or open, which again, the 0.33 is just 1 minus the other one, because these will always add up to 1. And then after a light snowfall, schools are closed 3% of the time. Closed is 3. Open then would be 97 or 0.97. So once those are all on there, okay, and set, let's say a question was asked, find the probability that the snowfall is light and that the schools are open. So what I would do then, and I kind of am getting a little bit of help here, snowfall is light and the schools are open. So I'm light and I'm open. Each event that happens here gets multiplied together. So whenever we're doing one of these, when we're working left to right, we multiply. But if we have things we're trying to add together that are going downward, that's when we're going to add. So, to calculate this, I'd take my light number, and I would take my open number, and I'd multiply those together. So each branch that you continue to go out to, you keep multiplying the branches together. And so when you do that, and if I turn that back into a percent, it's about 92. Okay, so we just multiply the branches together, and that should get us into pretty good shape as far as that goes. So what I'm going to do, and we're going to flip over to that here. So this note sheet, we're going to keep close, but we're going to move it here. It's going to get us thinking about this worksheet that goes along with it. So what I want to do is I just want to do a couple of problems on here that I thought may either cause some dilemma or just to kind of give you a little bit of review on some things. So let me go ahead here. I'll grab one thing here quick. I was going to grab one thing quick, but we'll just keep rolling for right now. I'm going to have to grab a calculator. So we'll go ahead, we'll add our columns up here, like we normally do, because we're never sure which part of any of these columns that we may end up needing to use. And I'm going to shrink for just a sec here. Anytime I see a table, that should be my first step. is to go ahead and add horizontally, add vertically, and then see if all my values add up in the middle, which they should. Yep, 224. Yep. 4 didn't quite come down there. So now, depending on which type of question I'm being asked, so let's say, for instance, I don't know, A. Employee has less than a high school education. Notice there's no slashes, there's no givens. So here, I look and I go, okay, well, it doesn't give me a given, so I guess it's out of everybody. So that's out of 1,200. The employee has less than a high school education. So that would be any of these people. And that's all I would need. Now maybe we add a little more to it. Maybe we get something like C. Employee earns over $30,000 and has less than a high school education. We still don't have a slash saying given. So we're still going to be at a 1,200. But there's a compound portion to this now. Employee earns over $30,000, so we're going to be in this column, and has less than a high school education. So that's the only part of this one that would work, that little number right there. And then maybe math enter just to make sure that I get the right value. But if it says and, you have to find the box or boxes that are true just for that particular part. However, a little more here. If we get to E, let's say, okay, there's the slash now. So now we're doing the A-B stuff. So we're like, okay, so probability of high school education, and then up top would be over 30K in a high school education. So you notice the way that it's worded kind of depends on which values I need to use. So high school, 224. Then over 30,000, so the last column, but the high school should be 14. And a little math enter action. And I'm set and ready to go. So that's kind of how those would look. And those are more like the ones that we were doing yesterday anyway. Now, the other one that I want to take a peek at on this side, because it's kind of weird, and I'm going to make note of one other thing that I forgot to tell you at the start. So let me go back to the top for just 1 second. Okay, on this one, we are going to skip 7 and 10. There's some issues going on with both of those that are just going to be a bit more than we feel like playing with. So, scroll back down here some. When we get to number 3, some of these started to get a little bit strange. So I wanted to do one of them. So let's go to 3B. Okay, the probability of getting a number less than 10 given the number is less than 13. What? Okay. So probability of less than 13, now this is the one that tends to blow people's minds. Probability of less than 10 and 13. So I start looking and I'm like, okay, the bottom I can handle. Probability of getting less than 13. So you can't include 13. So 1, 2, 3, 4, 5, 6, 7. Okay, there's 8 of those. Now the top, read it carefully. The probability of getting a number that's less than 10 and 13. So could I count 12? No, that's not less than 10. Can I count 11? No, that's not less than 10. 10 is not less than 10. Once I hit 9, 9's less than 10 or 13, and 8 and 7 and 6 and 5. So these 5 numbers cover both things, and that's how I would get to my answer. Nothing too bad, nothing too bad, nothing too bad. Issues so far, because I'm just trying to kind of get us a feel for all of this a little bit. I'm thinking in retrospect. Isn't it great when I think on the fly when we're in the middle of one of these things? All right, I'm going to make some of you real happy campers with me. You're like, you're going to add stuff to the stuff we don't have to do, aren't you? Yeah. I'm going to try to avoid some of the tree diagram stuff just because we're not going to get to spend the time on it that I want. You're like, Harty, this is awesome. You should do this in every assignment. You're like, there's 10 questions on this, and you're letting us skip 5 of them. This is great. Well, it's kind of like an even odds thing, okay? So 4, 5, 7, 8, and 10, that should get us out of all the nastiness and with all the tree diagrams, which will make me feel better. And I think otherwise, we should be good on you being able to do the other stuff, because everything else is just charts, okay, like the charts we've been doing with the conditional probability. And I've got a key up front for those, even though I will write the other values on here quickly. Okay. So then the only other sheet that you have that we are going to be dealing with today is compound theoretical. Now, this you chatted about last week on the day that I was not here. So I want to make sure we understand how this works. So it's notes on the front, and there's a few problems to practice on the back. So what we're going to do is we're going to basically look down here at the bottom, just what's going on in the boxes here. Hi. Alrighty. So independent events are events which the result of the first event does not affect the result of the second event. So for instance, if Susie selects 2 chips from a bag of red and blue chips, if she selects a chip, so let's say she gets a red one, and replaces it before the next selection. Because if she takes the chip she just got and puts it back in the bag, whoever draws next, even if it's her, has the same chance of getting all the chips that she did originally. So they're independent. It's not like, it changed her probability at all. Dependent, though, occurs when the first event does change the results of the event that follows. So, again, Susie's still selecting 2 chips from her bag of blue and red chips. If she selects one and does not replace it before the next selection, that would be dependent. So let's just say there were 10 chips in the bag. Okay? If she takes out a red one and keeps it in her hand, now there's only 9 chips. Now the odds have changed. Her probability has changed. Because in this case, there are less chips. Okay? So if it doesn't matter from one event to the next, cool. That's independent. If it does, that's going to be dependent. And what we're just going to do here for a minute, just to make sure we're kind of seeing how this goes, is do a few of these on the bottom and see, okay, what's the difference here? So when we're just going to lock in on independent and dependent as far as these go. So I look at this and I go, okay, on a shelf there's 60 novels and 20 poetry books. What's the probability that person A chooses a novel and walks away with it, and then person B walks up shortly after and picks another novel? If the first person walked away with theirs, is that going to affect which novel the next person can get? Yeah, if there's 60 books on a shelf and I pick one off and take off, that next person doesn't have a chance to pick that same book. So my probability just changed depending on what they did. But here, what's the probability of getting a 7 after rolling a single number cube, 1 to 6? Well, again, if I roll a cube, the next person comes along and rolls the cube. Is what I did matter? No. They're separate from each other. They're independent. So it's going to be little things that we're looking for in here. Numbers 1 to 20 are placed in a bag. Without replacing the first number, I took my number out. I got 7. I put it in my pocket. Okay? Now everything just changed for the next person. It changes so it becomes dependent. And we start to see, as we do these, okay, Diamond's playing a game. She has to spin a spinner that's divided into equal sections of orange, red, purple, and pink. What's the probability on her first spin she'll land on pink, and then red on her second? So if I'm spinning a spinner, and I get a color, as long as I don't take the color off the spinner somehow, I'm not quite sure how I do that, and I spin it again, all the colors are still going to be there. It's going to be independent. Okay, they're separate. And that depends on how we tackle these. So when you look at the back on this page, okay, just kind of getting you thinking about this and kind of playing with the values some. So when we get back here, let's actually do one of these. I'm going to grab a couple of these, I think. Ooh, I see. Okay, I see 2 I like. Okay, so let's try 11 and 12 here. What's the probability of rolling a 4 on a number cube and pulling a red marble out of a bag that contains 3, 2, and 5 yellow marbles? Okay, I got 2 events going here. I'm rolling a die, and I'm pulling a marble out of a bag. So we got to look at them separately. What's the chance of me getting a 4 on a regular die? 1 out of 6. Okay, so my roll would be 1 out of 6, and whenever you have multiple events, compound events, we multiply them. The next one's pulling a red marble out of a bag that has 3 red, 2 black, and 5 yellow marbles. Okay, we'll pull a red one out. I know there's 3 red ones. That's my success. How many marbles total are there in the bag? 10. So now, I'm just going to go ahead, multiply through, and do a little math at runner to get my answer. So it's compound, but they were independent events. What I rolled had nothing to do with what I got when I picked. Ooh, I'm going to change up. I'm going to go to 13 because I just saw something I wanted to see. All right, we got a bag of 17 colored chips. 4 are blue, 6 are green, 2 are red, the others are yellow. What's the probability of drawing a blue chip, replacing it, and then drawing a yellow chip? Okay, so let's see. So it looks like I'm drawing twice. So I got draw 1 and draw 2. I got 17 chips. What's the probability of drawing a blue chip? There's 4. Replacing it, so I took the blue chip that I just got and I put it back in the bag. How many chips do I have to pick from now? Still have 17. But now I'm drawing a yellow one. Ooh. How many yellow ones are there? Nice. Okay. Because 4 and 6 is 10 and 12. And the others are yellow. Well, if I already have 12, that means there's 5 left. Nicely done, nicely done. And I just multiply across. So that is what we're kind of playing with. So just play with the rest of these on this side. And then just playing with those 5 that are left in that worksheet 12-2, The keys are up here. I'll separate them so they're easier to see. And then tomorrow we will deal with experiments, surveys, and observational studies and kind of go back over some things again and get feeling comfortable for the upcoming quiz.